So hello everyone, I am Abradeep and I will be navigating from now, and we will be discussing here the different facets of additive manufacturing microstructure module of AM PravaH, a simulation software from Paanduv Applications. I will start with my introductions. So I am Abradeep and I am a material scientist working here at Paanduv Applications. I have my backgrounds with the additive manufacturing and the experimental microscopies. I have my background with the composite material manufacturing, and I have my backgrounds with the microstructure and process simulations, including the additive manufacturing processes that we have been doing here at Paanduv Applications. Coming to the microstructure evolution, for our microstructure module that is offered by Paanduv Applications, herein we will be delivering our microstructure module wherein we can show the spatial and temporal evolution of the microstructure. It includes the kinetic Monte Carlo model and Rosenthal's equation to generate the microstructure module. In this particular slide, what you can see is a microstructure that is formed for the 3-layer 3-track stainless steel 316L composite, wherein you can see we can easily dissect the different planes of the microstructure so that we can have an effect of tomographic data that we can attain from such type of analysis without delving us deeper into the 3-dimensional EBSD, which is quite a rare machine that we can have in most of the academic institutions. So combining this kinetic Monte Carlo modeling with the Rosenthal's equation, we provide a description of the microstructure developed during the process. So in a synopsis, what it provides us with is a 3D tomographic information along with the microstructural informations, which are the grain boundary distributions and with the grain sizes. Typically we can have different sort of sections that we generate through the EBSD data, and we can have a complete microstructure description with this particular software module. Some of the recent advances in AM PravaH software includes crystallographic texture. As we all know, having a crystallographic texture data without using an experimentation like EBSD or bulk texture analysis has been a challenge since its inception. With this particular advancement, what we have developed we track down the misorientations from the kinetic Monte Carlo and we put it in a stereographic plane, and we achieve this crystallographic texture data. We also have added another additional capability. Instead of using Rosenthal's equation to improve our microstructural accuracies, we can take the temperature gradients, we can use the thermal histories generated during the meltpool dynamics. Meltpool dynamics has been a USP of Paanduv Applications since its inception. In this module, we have simulated the meltpool dynamics first, considering all the physics-based considerations, including the Marangoni, including the recoil pressure and all those elements, and we included those temperature fields and we take out their gradient and we generate this sort of microstructure evolution. I will be navigating for the further slides using the case studies and validations that we have done to showcase the capabilities that we have in our microstructure module at AM PravaH. For the case study 1, I will be considering optical micrograph. So in general, when you have an additively manufactured component, we take it out and we do the basic microscopy. Instead of going to the EBSD based analysis directly, we can simulate the process. What we can do, we can have a nominal optical micrograph. We can measure the physical height and physical depth and width of the melt pool, and we simulate the entire process, and we can generate the pool of microstructures, a pool of molten metals. so that we can have what we have here is a single build, that is a single track analysis of the melt track for this particular module. So we can see here the width and depth analysis from the experimental and the simulation, and the error percentage that we have in our case is way below 5%, which is quite accurate. Taking these dimensions to be followed and using the Rosenthal's equation, we have developed the entire microstructure for 5-layered and 4-track simulation. In this particular aspect, we have studied the grain nucleation driven by the Monte Carlo model, which is a probabilistic model, so that we can generate the non-stochastic behavior of the additively manufactured microstructures. We can also see the subtle details that are captured here by using the fundamental equations. What we can see here, that grain growth that has happened for the for a certain crystallographic direction has a certain anisotropic characteristics. We can see some subgrains have formed in the front face of the meltpool structure. We can see here the microstructure that is developed here has a columnar front as well as some sort of needle-like cellular prismatic structures that has some epitaxial nature. We can also see that we have the grain size charts which can be used to dictate the Hall page strengthening, and using such equations we can have some idea about the yield strength, and we can predict the strength of the composite or strength of the material before we actually make it. Coming to the visualization part, in the visualization part we can see here I have sectioned the microstructure in such a way that we can see the 5-layer development here along with the 4 tracks, and we can see how accurately it has captured the transitions from the columnar to equiaxed in between the 2 successive melt tracks. We can also see the laser trajectory that it has followed alongside. We can also see the crystallographic texture presented in using the inverse pole figure without actually diving into the EBSD analysis. We can also see for this entire simulation, the computation time here is around 18 hours for a 48 cores machine. Such types of simulations have a great accuracy, and it also holds a thermal history quite accurately depending upon which the microstructure evolution has happened. That's how we have captured the not only the spatial development but as well as the temporal development. So these are the basic outcomes from this study, is that using an optical micrograph we can calibrate the meltpool dimensions, and therefore we can develop our own parameter sets that can be used for the optimization and narrow down the window, so that we can know how our operation should be, whether it should be in a conduction mode or in a keyhole mode. That we can determine easily. Based on that, we have developed the meltpool dynamic simulations, wherein the temperature fields and gradients we can calculate and track down for the Monte Carlo approach. Using this approach, we can form the entire heterogeneous microstructure that are commonly observed in additively manufactured metals, and therefore what we have is the complete description of the microstructure that is formed in the AM process. Therefore, we can confirm that AM PravaH microstructure module can be treated as a virtual twin for an exact microstructure evolution process. We can also predict the crystallographic texture and also predict the grain size. Therefore, it won't be wrong to say that we can shift the length scale from an optical micrograph to the EBSD level without considering that experimental challenges that actually occur, such as the data acquisition and data analysis part with the different sort of softwares that we generally do in our regular microstructure analysis. It gives us a shortcut, or it gives us a complementary data. That's what we are trying to come up with AM PravaH software. Another validation case study that I would be discussing here is that how accurately we can capture the melt pool dynamics, and also from that melt pool dynamics how accurately we can predict the microstructure simulations. In this, what we have a data from data that we have collected from a publication. Herein we have a certain microstructure that is developed for a single exposure, single spot in a laser powder bed fusion process. In this, we can see here the EBSD data shows there are some non-indexed points, and therefore there are certain areas which are not actually covered here quite properly. Alongside, we have the AM PravaH simulated microstructure. We have tracked down the entire melt pool dynamics, and for each and every point we have calculated the temperature field. Those temperature field data was collected and exported into the microstructure module, wherein we have converted that data into the conventional route, so that we can have a complete description of the microstructure morphology. Based on that, we have analyzed how the grain growth can be predicted and how it can be done, and how the microstructure simulation can be performed, so that we can have the closest of the accuracy. We can clearly see the analogy is quite remarkable. It has not only captured the uncaptured regions from the EBSD, that is the non-indexed points, but also it has captured the entire crystallographic texture that we can see that has developed in the EBSD microstructure. Herein I will be discussing about the mechanism. You can clearly see with the images here that how these multi-phase simulations are useful to decipher the actual microstructure evolution. You can see here how the microstructure analysis gives us the detailed insight about the formation of the microstructure, in which we can see how the vapor entrapped gas pores can be modeled using the four-phase multi-phase system that we generally use. To summarize it, we can clearly see what we have done is the high fidelity melt pool simulation, followed by the dynamic temperature field and solidification field data collection. Along with, we have used Monte Carlo nucleation and growth approach, and then we use these dynamic temperature field variables coupled with the Monte Carlo simulation to generate the entire microstructure. We can see how precisely it has captured all the different aspects without considering any sort of aberrations here in the microstructure simulations that we generally see when you go for there are different sort of artifacts that generally appear in X-ray imaging and that sort of practical characterizations that actually causes data loss in certain cases if the data is not properly well analyzed. Also, here we can see the computation time for such a great simulation is only 4 hours for an 8-core system, which is quite common these days. And this sort of simulations actually shows us how accurate we can go and how accurately we can capture the entire starting from the thermal history to the microstructure evolution. It captures the entire phenomena, and that's something that makes AM PravaH a phenomenal software. In a nutshell, what AM PravaH can do for metal additive manufacturing field is basically it uses the melt pool dynamic simulations and of the processes such as laser powder bed fusion. It can be any process that we have already demonstrated, like it can be LPBF, it can be WLAM, or it can be WAM, wherein we can solve the entire fundamental equations using the CFD approach and the basic and the fundamental approaches, and then we solve those fundamental equations and come up with the with the accurate melt pool dynamics without having any assumptions. Another predictions that we have done so far is the microstructure evolution, including that factor wherein the core of the dynamic temperature code is the dynamic temperature field gradients, which actually makes the data quite accurate. We can also see the crystallographic texture and grain size information that are trivial for the EBSD analysis only. Some other capabilities of AM PravaH microstructure module includes the microstructure evolution of using the Monte Carlo approach, which is a probabilistic model. Unlike other different microstructure models like cellular automata, it is not a deterministic one. Therefore, it gives us more clarity towards the probabilistic nature of the heterogeneity in the that are observed in the additively manufactured microstructures. It actually gives us a correlation between the process parameters and the microstructure information that you can correlate. The crystallographic texture is another insightful area that without getting into the complexities of the texture informations, which are often difficult for the users to analyze, we are directly feeding it into our systems so that it can not only generate the microstructure but also giving us the information about the orientations of the crystallographic orientations. Generating a microstructure from the dynamic temperature fields has been a great opportunity for the users so that they can put this same idea to not just the laser powder bed fusion but also the other manufacturing processes such as WLAM and WAM. This is something that actually provides us with the capability to be a digital twin of the entire additive manufacturing process. Other benefits that we have with AM PravaH includes it provides an end-to-end solution for the additive manufacturing process. That is, we are covering from powder to a part scale simulation. We can cut down the cost fundamentally by around 67%, and considering the initial process optimizations and other aspects that covers repeated trials and errors industrially and in the research principle. Also, we have 20 to 30% of cost saving in the material side, because with Paanduv Applications different approaches, we can not only simulate the spherical ones but also we can simulate different morphologies of the powder. That actually helps us to predict the microstructure and the meltpool dynamics of the non-spherical and irregular powder shapes. It can also reduce the failure rates up to 10% depending upon the recent capabilities that we have started with the FEA based approach, which includes the part scale modeling. So with that, we can, coupling with the microstructure data, we can have some idea about how the failure phenomena can happen. So based on that prediction, we can design our material and we can design the processes in that way so that we can save it from the premature failures. It also saves the experimental trials quite significantly because we can see here that without getting into different experimental methodologies, we can actually simulate that entire structure before we run into the microscope. Therefore, completing this, we can definitely say we can emerge ours as an virtual twin for the additive manufacturing process here in as an industrial process and as a potential tool for research in additive manufacturing. Here are the several users of AM PravaH. Here we can see the different global institutions that have acknowledged and recognized our contributions. Here are some defense organizations who have worked with us and are our happy customers. And we have some industrial collaborations and industrial customers from AMACE and InSmart Systems. I would like to thank my audience. I would like to thank my colleagues with whom and whose support has been and I am thankful to them for their unwavering support that they have provided for developing such innovative modules and developing such innovative work here at Paanduv Applications. Thank you. You can request a demo for our particular software by clicking on that link below that is added to the description. Thank you very much.